This lecture is related to the regression analysis. We'll be considering both linear as well as non-linear regression analysis. Now for this linear regression analysis, we have a very simple problem in our hand. That is, we have a polynomial equation which is defined over here as a pressure. The output pressure depends upon the function, independent function, temperature. Now this is a simple polynomial equation where all a1, a0, a1, a2, a3 and so on till an, all these are the constants, and n represents the degree of the polynomial. So we need to calculate all these constants and we need to restrict the value of n so that our RMS, that is root mean square, comes out to be the minimum. Now for the data, that we have the data over here in our hand, that is the temperature values and correspondingly the pressure values, which we have taken from the paper Pressure of the Benzene from the Paris Handbook of Chemical Engineering. Now why T over here is the independent data, pressure is the dependent data. So this, let's say, is the X values and this represents the Y values. So let's transform these values into the MATLAB and try to get the values of those constants and calculate the RMS. So first method which will solve is the linear regression. Okay, so first let me put the pressure values over here. So these are the pressure values we can see over here, 1, 5, 10, 20. Okay, then and now we're going to put the temperature values. We have the temperature, you can see the temperature. Okay, now let me define the value of n which I want. Let's start with the basic one, cubical. I want cubical value. N can be 2 also, n can be 3 also, n can be 4 and so on. Okay, so let's assume that the polynomial function is a cubical and we'll compare with the higher order of cubical. So we use a command that polyfit T, that is on the x-axis, P on the y-axis, and M is testing. Okay, small. And moving further, now let's evaluate. Now this polyfit has been done. Now we need to calculate Z. That's the poly valve E comma whatever the equation that has been calculated by the coefficients E. Now this poly valve will evaluate using those variables with the different value of T's the value of Z. Now we'll compare the Z value, that is the calculated value, with the experimental value which has been listed in P. So we'll use a normalize P minus Z, capital Z, and normalize it. Okay, then we calculate the total number of variables in the P. So P length, that is done. Now we write RMS. RMS will be norm P minus capital Z by square root of n, small n, done, and enter. So the RMS comes out to be 4.5247, and if we want to see the values of those variables which E has calculated, these are those coefficients. So this is A0, this is A1, this is A2, and this is A3. Now let's see the plot for this thing. So we'll write a command plot capital T minus capital Z. Let's differentiate with the small variable O. Capital T minus capital P, comma So you can see the circle ones are the values which has been experimentally calculated using this correlation, and the dark line, the black line, shows the values between pressure and temperature values corresponding to this thing. Okay. Now again, if we try to change the value of m, so how does this thing goes and thing? For that, what we do is, let's copy this entire program and paste it in the m file. So let's create one m file for us, so that will be easy for us. So let's write a linear underscore regression. So we created an m file for us. Now further, and let's close this and RMS system. Now we give this command also plot, so that we differentiate the plot values. Now I can change the value of up to 4, and I'll move this also. Now when we run this, we can see they matches exactly. Further, the RMS value decreases, whereas in the case of when m was 3, it was 4.5. now RMS decreases 0.46. Now to what extent we can decrease the value of RMS? So the question comes, now if I randomly put a value over here 7 and run this thing, you can see the curve fits better, but RMS also decreases, but it shows that the polynomial is badly conditioned. So the condition number is not good in polynomial. Further, if you see the coefficients of E, 1, 2, 3, 4, so constant A0, A1, A2, A3, apart from A3, all the coefficients A5, A6, A7, A10, all are appearing to be zeros. So there is no usual way to extend up to higher powers of n. So you can keep up to third order, fourth order, or even the fifth order. So you can clearly see this thing. Now let's suppose if somebody says, okay, let's go for the quadratic expression, whether the quadratic expression fits better or not. For that, I've replaced m by 2 and run this. You can see there's a difference, and the RMS value is around 20. So for m equal to 4, we have the better result, that is 0.464460, and these are the coefficients. Further, the graph fits properly. So this is how you do the linear regression analysis. Now let's try a non-linear regression analysis. Try to fit a non-linear. For non-linear, let's say we have an Antoine equation with us, which is log of p equal to a minus b by tc. Now this is a non-linear regression. We'll try to fit, we know the value of different p's, and I'll try to evaluate a, b and c. For that, we'll be using an inbuilt function of MATLAB, that is L square curve fit, that is least square curve fitting, which is normally done for a non-linear regression. For that, okay, we'll create a new, let's create a new m file. Created a new m file. Okay, now we'll paste those pressure terms and temperature terms in that m file. Okay, now temperature was the x-axis and pressure we know is the y-axis. So we can again, we can use this as a command. We know that which pressure value will be what. Now we can say x data, that is the temperature value, and we'll define this temperature values in the x data. Then similarly, y data is equal to our values of pressure in y data. Then let's give some initial values to those a, b, c randomly. It's some initial value because the program will run only if we give some initial values to a, b, c. So for a, let me give 5, for b it's 500, and for c let me give it around, okay, for b let's take it 1500, and it'll be easy. C is around, let's say 200. Now we'll write x comma this norm, that is, we'll calculate the regression normal equal to L square the fit. Okay, but before that I have to define my function. Now this says define your function. X naught we have defined, X data we have defined, Y data we have defined. Now we need to define a function. For that I've defined my function over here. Now this is my function. Now we know that our expression was log 10, log to the base 10 p is equal to a minus b by tc. Now this can be modified, so p can be written as 10 raised to power this entire expression, that is this. So the function f is 10 raised to power x1 where x1 is a, x2 is where b, and x3 is c, that is your x data x3. Okay, so this is my function, and which has been stored by the name of my fun. So I'll write this my fun over here. So at the rate my function, okay, done. The x naught values, okay, done. The x data, okay, done, and the y data, done. And we'll save it by some name, which we name it as non-linear regression. Done. So when we run this thing, so it will display the result at my command window. So it says that optimization terminated, relative function values have been created. So the value of a comes out to be around 6.6, value of b comes out to be around 1053, and value of c is 2000, and the resonance is this. So this is how we do calculate, the functions a, b, c using nonlinear regression. I hope you like this section. Thank you. Please do comment. Thank you.